Hello and welcome to my channel. I'm going to try something a little misguided, perhaps even ill-advised tonight. I'm going to try something in the vein of what I'm going to call fantasy film and physics. That's right, this is the famous bad handwriting of the very fast writing science teacher. I'm going to be trying to do some physics where it is totally inappropriate in the fantasy literature and big budget film of The Lord of the Rings, and in particular the famous Balrog versus Gandalf fight. Now, this is a scene which involves a lot of free fall, which is very simply described by some equations that I teach to my high school physics class, and so it's pretty boring to do, this is a physics problem kind of exercises where it's just such and such is going this speed at such and such a position and such a time. Tell me what happens next. That's really boring. It's a lot more interesting to give a situation that the students can explore, almost more like a sandbox game than a linear point by point kind of plot line. So what I'm going to do is I'm going to let this scene unfold naturally as it does, and I'm going to try to keep my camera in focus. Quite annoying. And as it does, I'm going to explain the physics that's going on, how we would be solving it at a high school level, and the things at more of a college level that we'll be ignoring right now. And also, I'm going to see if I can't kind of bridge the gap between what we are doing and what we should be doing. That is, trying to do physics on a movie is completely inappropriate. This is the kind of Neil deGrasse Tyson thing that nobody likes and everybody finds annoying because we're trying to, correct mistakes in a movie. No, that's not really what I'm after here. What I'm after here is that I am a science educator, I'm a physics teacher, and so part of what I'm doing is not just equipping future STEM people, people whose careers are going to be in STEM, scientists, mathematicians, teachers, whatever it is, to, be equipped for their future careers. I'm also trying to add a scientific, analytical dimension to the way that everybody thinks. And while that may perhaps limit your enjoyment of certain unrealistic things that you see in fiction, it may also heighten your awareness of certain things in your daily life. Now, those of us who are accustomed to the suspension of disbelief for the purposes of fiction should not have any problem with this. After all, we are looking at a giant smoky fire darkness monster, and we're kind of just okay with that. So one thing that we need to make sure of is that we are being generous with the depiction of time here. For example, physics treats time as just another quantity that we need to measure, and as we are going back and forth between one cut and another, time may not be exactly literal. Alright, so we got some physics going on here. I think I better pause the video real quick. So as you see here, we got a little bit of what appears to be possibly slow motion, but if you look at how Gandalf's hair is kind of blowing around in the wind, I don't know, that looks like it might be real time. But then it goes back and forth to like reaction shots and, back and forth. So time may not exactly be literal here. We're going to go with it. So we're just going to assume that time is literal, and that just is going to make things a lot simpler. So let's go back to, here we go, the beginning of free fall. So noticing here, Middle Earth seems to be a lot like Earth. Everything looks normal, gravity looks normal, and so as soon as I get a little something going on here, then I'm going to pause and tell you what is up physics-wise. All right, there we go. So we have a bridge starting to collapse. So moving past fantasy, film, and physics, boy, I really wrote that terribly. We've got a free fall situation. So here's how free fall works from a high school point of view. If you go up to higher levels of physics, you're going to start treating gravity as like curvature of space-time, and all falling paths are actually like, straight paths through curved space. Yeah, that's not what we do in high school. You see, One thing that fantasy and film and physics all have in common is metaphors. You see, fantasy and film literature tend to use literary metaphors in order to describe the real world. In physics, we use mathematical metaphors to describe the real world. So here's a very simple mathematical form. I might just describe a parabolic shape, and I might say something like x equals a over 2 t squared. Okay, so that is a mathematical expression. It is a function, it's a quadratic function, and it's the kind of thing that produces a parabola. Okay, cool stuff. What about it? Well, it just turns out that this behavior, the behavior of this function, happens to be the same behavior as the things that fall or fly through the air. So when this Balrog is flying, or falling I should say, through the mines of Moria, this is going to be a really good description of it. And so if you don't mind, I'm going to describe it like it's a metaphor, and I need to be able to Mad Lib style fill in some of these adjectives and nouns. So this expression here says basically that the distance that you move while accelerating while time passes is described in this way. This is how far you go, this is how long you've been going, and this acceleration basically is an expression that describes the change in your speed. Now, when the Balrog was standing up on top of that bridge, it was not moving at all. And a moment after it falls, it is now moving, which means its speed has been changing. Since its speed is changing, we say it's accelerating, and for complicated reasons that I might describe later, this is the proper way to describe that motion. Since, as I mentioned, it seems like Middle Earth is very Earth-like, I'm going to go ahead and say that the acceleration in Middle Earth is equal to that which we find in Earth, and that would be 9.8 meters per second per second. And so that means that every second you speed up another 9.8 meters per second. And just in case the metric system is not your cup of tea, 9.8 meters per second is basically a good, safe parking lot speed. Okay, so now that we've got that established, we got this Balrog falling. We want to know how far he's falling, maybe, so we need to know how long he's falling. Fortunately, this is a video which has timestamps in it, so let's see. The bridge starts to collapse here, and that time is going to be 3 minutes and 27 seconds. That's what my video player says right now. Let's see how long this guy falls before something else interesting happens. So, falling. And there's nothing holding it up. It's just completely at the mercy of the gravity of Middle Earth. And so Gandalf was like, all right, I got you there. And all of a sudden, nope, actually, okay, so something has just happened here. Just in case I lose track of this, I want to make sure I note the time now. At this point, the Balrog has fallen some distance, caught Gandalf with its fire whip, and right now the time says 3 minutes and 42 seconds. Now, right now, I already have a problem, and I just want to give you a little hint as to how physics problems are solved. I'm using T to refer to time, but I've got 2 different times. How am I supposed to keep track of which time is which? One thing that you can do is treat math like a language. If time is a noun, I'm going to give each one an adjective so I can keep track of which is which. And the way that we do adjectives in mathematical expressions is with a subscript. So I can say this will be time 0, and this can be time 1. And basically, I can make a list of all the times. I can say that this is the initial time, and this is the first time after the initial time. Think of how floors are numbered in certain countries where we have a ground floor and then a first floor. It's pretty similar to that. So I've got two different times. Now, the duration, that would be the difference between those two times, is really what's important. In other words, how long was it from 3 minutes and 27 seconds until 3 minutes and 42 seconds? Well, just in case you are not a fan of doing math in your head, or perhaps if you are doing this on camera and you're really insecure about doing it in your head, making a mistake, we can use calculators, not a problem. So I'm just going to do 42 minus 27, 42 minus 27, 15 it is. So that is a 15-second difference. If you're falling for 15 seconds, we have another way to notate that in physics, and that would be with the use of this Greek capital D, aka delta. And when you use a delta, what you are saying is you are referring to a difference between two consecutive values. So this delta t is going to equal that time minus that time, which is a grand total of 15 seconds. Now, here's what I've got. I've got this equation that describes the behavior. I've got this number, which fits in there, and I've got this number, which fits in there. If I rewrite this equation but use those numbers, here's what I get. I get the x, which I still don't know, but that's equal to this fraction, which has a 9.8 on the top, a 2 on the bottom, and over here a t squared. That would be 15. 15 squared. That is not going to be a small number. So clearing this, hold on a second. Now. Phone, now's not a good time. Okay. Clearing that. 15 times 15. That's not a 15, that's a 25. 15 times 15 is 225. That would be this bit here. 9.8 divided by 2 is 4.9. So this is going to be the same thing as 4.9 times 225. And that, I know you can do it on your own calculators at home, but if you just see the number come out of nowhere, it might look kind of confusing. 225 times 4.9 is 1,102.5. 1,102.5. 1,102.5. Okay. I want to make sure that this number is put into the proper context. This is a distance, which means that assuming that this was meters per second squared and this is seconds squared, the units have worked out so that this is in meters. Friends, this is more than 1 kilometer. This is 1.1 kilometers, in fact. That is extraordinarily long. Now just think about what this means. If you fall for 15 seconds, you will have fallen for more than 1 kilometer. But even more remarkable, if you fell with a fire whip in your hand and you can reach up, apparently with the end, and catch a gray wizard by his foot, your whip is at least 1 kilometer long. Now, I believe we saw this whip before. Let's see. Here, maybe? Does that whip look 1 kilometer long to you? It doesn't look 1 kilometer long to me. But hey, it could be a magic whip. I'm just saying, if this Balrog fell for 1 kilometer and still managed to reach Gandalf with that whip, that thing had to be 1 kilometer long because that's how far he fell. Was that a comment on this physics? Maybe not. Okay, so let's just relive those 15 seconds again. So during this 15 seconds beginning now, this Balrog would fall 1 kilometer, except that I am missing one crucial part of the physics of Middle Earth, and that is that Middle Earth is still full of air. So how fast is this Balrog falling right now? For this, I'm going to need a new sheet of notes. So I mentioned that acceleration is a change in velocity. Acceleration literally is just the change in velocity as time changes. If I were to write that acceleration is the change in velocity as time changes, that's what it would look like. Now, if I want to know how fast this Balrog is falling, again, just knowing that the acceleration due to gravity is 9.8 meters per second squared as it is on Earth, and that this poor, I don't really want to describe the Balrog as poor, that this cursed beast is falling for 15 seconds. That's 15s, just in case my handwriting is too opaque for you. I'm looking at this. A equals unknown speed change divided by 15. In order to solve for this, I need only multiply both sides by 15. And so if I'm trying to find out how fast it's going, I just need to multiply 9.8 times 15. That is 147. So I could say not only does this Balrog fall 1.1 kilometers during that initial 15 seconds, but it accelerates to a speed of 147 meters per second. And here's where we have a problem. You see, that kind of speed is unachievable for something of that size and shape falling through the air because of something called terminal velocity. You see, terminal velocity works like this. The air is full of, well, air. That is, individual molecules of air. Nitrogen, oxygen, carbon dioxide, water vapor, you know, the things that are in the air. Whenever any object moves through the air, in order to do so, it needs to push those particles out of the way. But every action has an opposite and equal reaction, which means those air particles are pushing right back on that object. And that's fine because the Earth, or Middle Earth's gravity, is pulling down on that object, and so it's able to push through. But the harder the object pushes through the air, that is, the faster that it pushes through, the harder the air pushes back. And eventually, they're going to be in equilibrium. The gravity of Middle Earth, gravitational force will be pulling down on this falling object just as hard as the air is pushing back up on it. And at that point, you can no longer speed up. This is called terminal velocity. And if I'm not mistaken, the terminal velocity for a skydiver in a diving position is somewhere in the neighborhood of 75 meters per second. Now, I understand that a Balrog is not a skydiving human. However, in just a minute, we will see that Gandalf is free falling alongside this Balrog, keeping pace with it. So, by all appearances, it seems as though the terminal velocity of this Balrog is equal to that of Gandalf himself. So, the Balrog should never even be getting this fast. However, in order to account for the approach to terminal velocity, I'm going to need to be using like differential equations and really complicated math that no high schooler in the United States is doing. So what I'm going to do is, for the sake of mathematical simplicity and frankly humorous results, we will be ignoring air resistance entirely. After all, this is what physicists do, isn't it? We imagine everything is a point mass in a frictionless vacuum, and we just do that because it makes all of our math simple. Well, look, do you want it to be realistic or do you want it to be complicated? Actually, I don't know which one you want, but I know which one I want. I want it to be simple. So, realistic and complicated. That wasn't the choice. It was simple or complicated. The point is, It's late while I'm recording this, and I want the math to be simple. So we're going to just assume that the Balrog has fallen a total distance of 1.1 kilometers, and that it is now moving at a speed of 147 meters per second. Let us continue with this awful, terrible, tumultuous fall. If you'll notice, the Balrog continues to fall essentially unabated, and we have some potentially non-literal passage of time as it seems semi-slow-mo, and some reaction shots of Frodo and Gandalf. But again, we are ignoring all that stuff. One last shot from Frodo, and then Gandalf, oh, he lets go. Once again, I need to make note of a time. Oh boy, I threw it over here. Oh, here it is. So I had my initial time of 3:27. Next time of 3:42. I'm just going to make note of those. T0 was 3:27. T1 was 3:42. And now I have another time, and this is 4:03. So this would be Balrog begins to fall. Balrog catches Gandalf with his whip, and then Gandalf lets go. Just so we are clear, the Balrog has been falling this entire time, with perhaps a slight break here at 3:42, but it wasn't much of one. So for our simplified interpretation of the scene, the Balrog has been in free fall for what? 36 seconds? It's time to do a little math here. How far are you falling if you have fallen for 36 seconds? Once again, our equation was x equals a over 2t squared. If we are assuming an acceleration of 9.8 meters per second squared and a time of, I can hardly believe it, 36 seconds. 30 seconds would bring it up to 3:57. 6 more seconds would take it to 4:03. 36 seconds. Ladies and gentlemen, 36 squared is an enormous number. So let me get back to my calculator here. I need 36 squared. Believe it or not, I did not memorize my times tables up to 36. Oh my goodness gracious, 1,296. I need only multiply that by 9.8 over 2, which is 4.9. And we have here a total fall of 6.35 kilometers. That is unreasonably far. That is how far the Balrog has fallen since it began, and up until the point that Gandalf lets go of this ledge. That is incredibly far. How fast has it been going? Well, just remember this equation. If we want to know how fast, we're going to need to be multiplying this acceleration by that time. This is 36 seconds. The delta V is equal to the acceleration times the change in time. That's going to be 9.8 times those 36 seconds. And once again, if I let my calculator do that work for me, because why wouldn't I? 9.8 times 36 is 3. That is Mach 1 plus a few. So 352.8. Holy cow, 352.8 meters per second. So those of you who already know how to do some physics might notice I've been completely neglecting significant digits. And look, do you want the numbers to look impressive, or do you want them to look proper? Okay, I'm just trying to not worry about too many things. It's like I said, it's late. I got to teach tomorrow. I'm just trying to do some math for fun. Leave me alone. Anyway, having fallen nearly 6.5 kilometers and now falling at more than Mach 1, but there's no sonic boom if there's no air, Gandalf now begins to fall. And this is where the physics really goes nuts. This is actually the part of this scene that made me think I need to do some physics problems on this. Because Gandalf is now about to do something quite impossible. I understand wizards do lots of impossible things, but this is quite impossible. Starting at 4:03, here is what Gandalf does. Gandalf falls. And falls. And falls. Catches up to his sword. And then catches up to the Balrog. Now, to be fair, this Balrog has been falling for what is now nearly an entire minute. It has been falling several miles. Okay? In excess of 6 kilometers before he even let go. And now, at this particular time, which happens to be, I should index, I've already done 0, 1, 2, I can do T3, 4 minutes and 21 seconds. Gandalf catches up to this Balrog. I just need... I'm going to have trouble expressing what is wrong with this. The Earth, Middle-earth, is pulling on the Balrog and Gandalf proportionally to their masses, which makes them accelerate at the same rate. This is the old, Galileo on the Leaning Tower of Pisa experiment with the big rock and the small rock, and they both accelerate at the same rate. Heavier things do not accelerate at greater rates because the force is proportional to the mass. I keep saying the Earth. Middle Earth. Do I need to keep... I'm going to keep saying Middle Earth. Middle Earth is pulling harder on the presumably more massive Balrog, but there's more Balrog to pull on, so the acceleration works out to be the same. Gandalf should not be able to catch up to this Balrog because they should be accelerating at the same rate, and the Balrog's head start should be completely undefeatable. However, I don't know if it's like some magic or maybe just the fact that this is like, a fantasy novel and not a physics textbook that maybe makes physics not work. Okay, fine. Sure, whatever. Gandalf is going to catch up to this Balrog at 4 minutes and 21 seconds. So, this is the most complicated problem of this whole set, and one that worries me a little bit because this is the one that I did not rehearse before I made this video, and that is, what acceleration must Gandalf have had in order to catch up with the Balrog? So, to be clear, Balrog began falling at 3:27. It has been falling until 4:21. That is a grand total of 1 minute minus 6 seconds. That would be 54 seconds. So, here is your ultimate train leaves Chicago, train leaves New York question, but for Middle Earth. So we've got a Balrog that falls for 54 seconds. 54 seconds, very long to fall. How long did Gandalf fall? So these times were Balrog begins to fall, Balrog catches Gandalf, Gandalf falls. Gandalf has only been falling since 4 minutes and 3 seconds, and it is now 4 minutes and 21 seconds. 3 and 21, there's a total difference of 18 seconds. Gandalf falls for only 18 seconds. And yet somehow they've started in the same place and ended in the same place. And that means they've covered the same distance in 2 different times. Now, if I were to say x equals a over 2t squared, remember that was our equation for the distance that you cover while you're accelerating over time. This would be for Gandalf. And let me just use a different color. I think I'll use red because the Balrog is all fiery and stuff. This one is for the Balrog. Now, they have different times. They have different accelerations, but they both have the same distance. Whatever that distance happens to be, not really material here. All I know is they fell the same distance. Although I am curious. Balrog, you fell, accelerating at 9.8 meters per second squared for a grand total of 54 seconds. How far have you fallen, Balrog? Balrog, how far have you fallen? 54 times 54 times 4.9, 14.3 kilometers. Holy cow. Can you even think of something that is 14.3 kilometers from where you are? It's quite far. So I'm just going to go ahead and write 14,288.4. So that's how far the Balrog has fallen at this point. We know that Gandalf has fallen the same distance because they've just met. They are in the same place, but at a different time. That time happens to be 18. So this will be 18 squared. That's the t, right? The one thing we don't know, though, is the acceleration. And we do know that this is equal to 14,288.4. So if we're trying to find A, what I'm going to do is I'm just going to do a little bit of algebraic rearrangement and say that this is A times 18 squared over 2. Now I can simplify that. I did not learn my times tables up to 18, so I'm going to have to see what 18 squared is. 18 times 18 is a lot. It's 324, but this is 18 squared over 2, so I'll just divide that by 2. It's 162. So this is 162 times A equals 14,288.4. Hey, if I'm trying to find A, that's not hard now. I just need to divide both sides by 162. And if I do let me clear that first. If I do 14,288.4 and divide that by 162, I get 88.2. A equals 88.2. Guys, this acceleration is almost 10 Gs.
Here are some results from a search.
Thanks, Google. I don't remember asking. Back to the calculator. 88.2. You see, when you are subject to what are called Gforces, that means you are subject to accelerations which are multiples of that which gravity naturally does. These are typically only experienced by jet fighters, jet pilots who are pulling hard turns or, perhaps very, very enthusiastic roller coaster riders. I don't know. I'm a very risk averse person, so I'm not very familiar with these. However, 88.2 divided by 9.8 is I like when it's a whole number. That's cool. Is only 9 Gs. I'm sorry. Only 9 Gs is 9 Gs. 9 Gs. So, unless I am mistaken, a fighter pilot pulling a turn or loop that undergoes 9 Gs will probably black out. That is the force of the centrifugal force from that turn. Hey, if you're like a physics person and you're watching this and you're like, centrifugal, oh, that's a virtual force. Hey, cool it. I'm talking about from the pilot's frame of reference. Just calm down. Just calm down. I know he's like accelerating, so maybe his frame of reference isn't valid. Just stop. Just stop. The force, the virtual force that seems to be draining the pilot's blood from their brain down to their feet while they're taking that turn is enough to starve their brain of oxygen and make them black out. So, in other words, the dive that Gandalf is doing right now is one of the most, like, amazing Top Gun, like, dives that any fighter pilot has ever done. And, frankly, if you were not impressed with Gandalf before, maybe now you should be, because apparently he's a top-rated fighter pilot who can withstand enormous G-forces. There's really only one more time that we need to be concerned with, because if you'll notice, they're in free fall this entire time. And here's where I'm justifying my terminal velocity, because Gandalf appears to be falling like this, in the head-down kind of diving, skydiving position, which gives us the terminal velocity of about 75 meters that I cited earlier. Now, clearly from this scene, they're not accelerating, they're falling at their terminal velocity. They're going to splash into the water at the bottom of the mines of Moria, and I meant to freeze on the splash, but instead I got this kind of weird picture of Frodo, I think? Anyway, our time is now 5 minutes and 14 seconds. So, to review. If you've been watching this video the whole time, you either really love physics, or you really love The Lord of the Rings, or possibly you really love me. And I don't know which of those is the best, honestly. It's probably not that last one. So here are the times that have been noteworthy. I'm just going to make note of them so that we can get everything straight. So we had a T0. That was when the Balrog started to fall, and that was at 3 minutes and 27 seconds. Then we had a T1. That was when the Balrog caught Gandalf's leg with his fiery whip. Then we had a T2. That was when Gandalf let go. It said, "Fly, you fools," which is kind of not a very nice thing. Just imagine if that was like his last words to the Fellowship, and it was just like, "You fools." And like that was just like sitting in the back of their head the entire time. Like they're trying to move on, kind of like, remember Gandalf as an inspiration, and, kind of take courage from him lending his support to the Fellowship. But like just in the back of their head, like, the last thing he said was, "You fools." That would be really discouraging. Anyway, just a reminder, the next time you are parting ways with someone that you really care about, pay attention to the last thing that you say to them. Maybe it doesn't have to be "I love you" if that's weird between you and that person, but like, let's let it be something positive, something that if it was the last thing you ever said to them, you'd be okay with it. Anyway, moving on. This is the time at which the Balrog began to fall, caught him with the fiery whip, Gandalf let go, and then we have our catch-up time and our last time. This is the time where they finally end their fall, because they've fallen as far as they can into the water. This is an enormous amount of time, from 3 minutes and 27 seconds up until 4 minutes. That would be 33 seconds. So up until 5 minutes, that would be a minute and 33 seconds. So the remaining would be 33 plus 14, that would be 47. This is a minute and 47 seconds of falling. Just now that I've said that out loud, I have this terrible insecurity that I've done that math in my head completely wrong. So if you don't mind, I'm going to double check that with a piece of technology that I implicitly trust. So yeah, that would be the 33 seconds until 4 minutes. Add 60 seconds. Now we're up to 5 minutes. Now 14 seconds. Yeah, 107 seconds. That would be 1 minute and 47 seconds. If you fall for 107 seconds, you will have fallen. I'm scared to do this. 107 squared times 4.9. 56.1 kilometers. Remember, this is in the absence of air resistance. Being more realistic, if they had achieved a terminal velocity of 75 meters per second almost immediately, and then fallen for 107 seconds, we would be looking at a very, very different distance. You see, when you're moving at a constant velocity, all you've got to worry about is this. If we are moving at a constant velocity of, say, 75 meters per second, our terminal velocity, and we're doing that for a time of 107 seconds, I mean, it's still a lot. But this time it's only 75 times 107. It's only 8 kilometers. So, really, the difference between air resistance and no air resistance over this time period is a factor of like 7. Quite a lot. So, most of the time when you're doing problems in a high school physics class, you're not doing free falls that last almost 2 minutes. And so air resistance is not supposed to make that big of a difference. But we're doing physics problems that maybe we shouldn't be, so that's why it made a difference this time. Anyway, so we've got a fall of 56.1 kilometers. I am a little curious. What was that top speed? If you fall, remember we've got an equation. Let's see here. It was delta V equals A times delta T. This would be 9.8 times 107. Trust me, that's a 7. That's probably how I write 7s. Let's see here. 9.8 times 107. 1,048.6 meters per second. That's absolutely incredible. 1,048.6. If I were to divide that by 343, I would get the Mach number. That's approximately Mach 3. Oh my goodness gracious. As opposed to a fairly constant velocity of 75 meters per second from air resistance. Okay. Why on earth would we do this nonsense? So here's why. One, because The Lord of the Rings is awesome. Let's just admit that, right? The Lord of the Rings is awesome. And if you're going to be doing physics problems, you might as well be doing it about something that people care about. Now, here's the deal. Real life is pretty interesting. But if you're going to do physics properly about real life, you need to be doing it with so much mathematical complexity that's like impossible for a high schooler to do it. So the idea is basically you can do your physics completely realistically with super complicated mathematics that, it's like be on the college level, or you can model the universe like that. So basically, these equations, right? This one, that one. These are the stick figure cartoons of the universe. Sometimes a stick figure is all the picture that you need, but of course there's a whole bunch of stuff missing in your stick figure cartoon, and it's just a matter of how picky do you want to be that it's missing. Sometimes you want to have it missing for comedic effect. For example, I think it's hilarious to think that the mines of Moria were 56 kilometers deep, and that the Balrog fell for a full kilometer before catching Gandalf with its fiery whip, which was a kilometer long itself. I think that's funny. I think it's funny to think that Gandalf performed some sort of 9G commando super dive on the way down to catch the Balrog. That just seems humorous to me. And of course, it's only humorous because it's completely ridiculous. This is a completely inappropriate analysis to be doing on this movie, on the story, but like, that's part of what makes it funny, right? Is that this is a completely inappropriate analytical tool for this. Anyway, if you're curious about why these equations exist, why they are what they are, hey, that's a topic for another video. But for now, I'm going to just sign off like Gandalf the White just did and say, if you liked The Lord of the Rings and I ruined it, sorry. If you liked physics and I made it boring, sorry. If you don't like physics but I made it interesting, you're welcome. And if you didn't like The Lord of the Rings and somehow this made it interesting, dude, what's wrong with you?